presentation, and he's also going to be graduating in the future, in the near future. So if you're interested, you can talk to him afterward. His talk is called JSWhiz, Static Analysis for JavaScript Memory Leaks.
Thank you very much. Good afternoon, ladies and gentlemen, and welcome to my presentation today about JSWhiz, Static Analysis for JavaScript Memory Leaks. I'm from Purdue University, but this work was done while being an intern at Google under Robert Hunt. So to give an introduction and motivation to this project and why we actually created JSWhiz. So back in March last year, Gmail's JavaScript memory usage was bad. And what do I mean by bad? So if we look at over a period of time, the memory usage for different kinds of users. While the median, on the median, this bottom line would represent the median JavaScript memory usage for Gmail. But we did find that in the 95th percentile and 99th percentile, some users are experiencing memory usage up to 10 times higher than the median when using Gmail. Now, given the size of Gmail, this is actually a fairly large group of people. And I would also feel very confident in saying that a lot of the people in this 99th percentile are some of those in this room. This is simply as Gmail is one of those applications that we run for a long time. I mean, I know myself, I've left Gmail running in a tab while traveling between 3 different continents. And then if you have a memory leak, you will show, over a couple of months, your memory usage will significantly increase. So with sort of this data, the Gmail performance team was tasked to reduce Gmail's memory usage. Find out why some users are experiencing this high memory usage and try to reduce it. So back in March of last year, a hackathon occurred between the Chrome and the Gmail team. They sat together and they developed a methodology to track these leaks, improve the tools by which to triage them, and they found around 30 leaks which they fixed and put into production. But this was still a very manual and laborious task. It required looking at the data logs and from the actual execution numbers and memory usage, trying to reverse engineer it back to where in the actual source code these occurred. And so that brought us to sort of the initiation of the JSWhiz project. The JavaScript as it's used at Google uses the closure library for which there is a compiler. So can we get the compiler to help us in identifying these memory leaks? So I started by presenting an overview of the motivation for JSWhiz. And in the next couple of slides, I'll detail the patterns we have found that leads to bloat, then present JSWhiz, and then present some results on the benchmarks internally at Google. So, like I said, it's an overview of the JSWhiz project. So JSWhiz, the idea was to create a compiler pass to statically find memory leaks. So we start with the results from the hackathon. And what I mean with the results is, I mean with the leaks identified, as well as the fixes produced by the Gmail engineers. These were the results we used. So it's very data-driven. I'm no JavaScript expert. We looked at what these JavaScript experts found to be the problem and how they fixed it, and we used this to extract patterns for which we can identify in the code potential leaks, as well as provide the programmer with a suggestion of how to fix this. So we identified 7 patterns, which I'll explain in the next couple of slides, but before I do that, I just want to go through a brief slide of some JavaScript closure terminology that I'll be using in this paper. So the important thing to think of when you're thinking about a JavaScript application is in the memory usage. So the memory of a JavaScript application consists both of the JavaScript object as well as the DOM, the document object model. So these are the buttons and the dialog boxes that the user sees. Well, we have like this button, the actual variable used in the JavaScript code. Event listeners are used to tie the DOM objects to the functions to respond to activities by the user. So if the user clicks on this button, the event listener is responsible for activating the required function. And then in Closure, we have event handler. Now, as per the documentation, an event handler is a superclass for objects that want to easily manage a number of event listeners. So this is a way of, you have a dialog box. This dialog box consists of buttons, text fields, checkboxes, whatever. An event handler is a way with which you can easily activate and deactivate these event listeners in this event. And I just also want to mention, Closure is an overloaded term in this presentation. There is both the Closure library, which is used to write JavaScript code which is in a browser-independent manner. The Closure compiler, which takes this code written using the Closure compiler, perform some type inference, some error checking, and some code modification. So it introduces the code, performs some inlining to present a streamlined JavaScript application that gets delivered to the user. And then finally we have a closure, as in the programming concept of a function and its referencing scope. So from the almost 30 leaks identified during the hackathon, we identified 7 general patterns of these leaks. These 4 patterns can be divided up into, these 7 patterns can be divided up roughly into 4 classes, which also corresponds to the techniques by which we find them. One is not disposing of event handlers, event handler member of an undisposed object, overriding event handlers in a derived class, and then unmatched listen-unlisten calls. So if you look at pattern 1, and the source code I'll present here were actually from the original hackathon, just sufficiently obfuscated, so to not get me in any trouble. So the first pattern is to create an event handler object without disposing of it. Very simple instance. You create, so this is the JavaScript approach of actually creating a new object of type of online handler. Online handler extends the event handler class, so it's a subclass, and we assign it to a local variable, online handler, which is then further stated as the online handler for this specific class if the user has a specific feature. But even though it's created, there is nowhere in the code where this event handler created is actually disposed of. And to just sort of give an indication of sometimes how easy these fixes are, and in this case, the way this leak was fixed was simply by inserting a register disposable, by registering the online handler as disposable. This associates the lifetime of the event handler with that of object ABCD, so that when the instance of ABCD is disposed, the event handler itself is disposed as well. The second pattern we found was setting a member object to null without disposing of the object. Now, in JavaScript, setting an object to null is sort of the idiom for you can reclaim this memory. But if you're working with event handlers or object with event listeners attached to it, then this is not sufficient. There are additional references kept to these objects, which you have to remove first before the garbage collector can actually take care of it. So just setting the object to null is not sufficient. You have to actually dispose of it before. The third pattern we found, which could actually lead to quite significant usage, was the object graveyard. This is an instance where the user creates eventful objects which is added to a bigger data structure or an array. These objects do get freed eventually. But just because they get freed eventually is not sufficient to avoid bloat. Many of these objects remain past their useful lifetime, past when the events they should have responded to are no longer triggerable by the user. These objects and the corresponding DOM remains referenced. The fourth pattern we saw was a local event handler. In this case, you create an event handler object locally. The reference to the event handler does not escape scope, so you have no way of later disposing of it because you do not have a reference to it. So you're creating it locally, but it doesn't escape, so you can't free it later. The fifth pattern is a little bit different. The previous patterns focused around event handlers and their derived classes. And the fifth pattern, we are actually looking at an undisposed object which has an event handler as a member. So here you have an object of class X, which in its constructor creates an event handler, which it does dispose of when the instance of X is disposed of. So what is the problem here? We are creating the event handler and we are disposing of it. Well, the problem is, the problem comes in when we create an instance of type X, but we now do not dispose of this type X. Because now every time we create an instance of type X, we are creating an event handler, but we're not disposing of that event handler as we're not disposing of that type of X. And then of course it's important to keep in mind, the way we see this are actually not from a JavaScript object leaking. These are very small. We see this normally in the data from the DOM objects that cannot be garbage collected because they're being referenced by these JavaScript objects. The sixth pattern we saw was overriding a private field in the derived class. I think this simply boils down to how object-oriented programming in JavaScript is different from in C++ or Java. If you override a field in a derived class, you're actually overwriting the parent. So in this instance, you have a type B that extends to type A. Type A had an event handler member, and which it was created in this constructor. But the moment you get to this call, you're overwriting the reference to the event handler of type A, of the parent's event handler. So the parent's event handler cannot be freed, or disposed of, sorry. The second pattern we saw is looking at unmatched listen, unlisten calls. So group event listen associates a JavaScript object, a DOM and a function call. Unlisten removes this association. And it's required for this to be successful, for a listen and unlisten to be successful, we need the signatures of both these function calls to match. Now the problem comes in with if you're using a bound or anonymous functions. These signatures do not match. These are actually completely different functions, signatures created by group bind, so they will never match. This is a special instance of having unmatched listen, unlisten calls. And the reason why we were sort of looking at specifically this special case is that in general, most modern JavaScript runtimes, actually most of those past Internet Explorer 6, are able to take care of unmatched listen, unlisten calls without it leading to memory bloat. But in this instance, this is still something where the programmer intended to do something which this call does not do. So in brief, JSWhiz is a pass in the closure JavaScript compiler. It performs static analysis of the JavaScript code to detect some of these memory leak patterns we just described. I would say it's reasonably fast. It adds about 3 to 14% overhead in the compilation time of applications consisting of many 100,000 lines of code. The runtime of JSWhiz is linear in the size of the AST, and I'll describe shortly how we perform it. And we detect about, I would say, 5.5 of the 7 memory leak patterns I've just described. The object graveyard pattern we cannot detect. The object graveyard requires additional semantic information. Just because you're putting event handlers or eventful objects into an array does not mean it's going to lead to a leak. For us to be able to statically detect that it's a leak or not, we need additional semantic information. We need to know when these objects are no longer needed, when these events can no longer trigger. And then, as I mentioned, we only partly addressed the unmatched listen unlisten calls, just simply as they weren't actually leading to any memory bloat. So these are sort of the 6 patterns we've identified. We are targeting in JSWhiz: create without disposing event handler, setting a member to null without removing the event listeners, a local event handlers, undisposed member objects which has an event handler as a member, overriding event handlers in the derived class, and in the unmatched listen unlisten calls. So basically we can divide it in 4 different techniques of finding these. And we noticed when we were looking at these that while we were focusing on event handlers, there is this transitivity. We are looking at, and the first 3 patterns lead to, actually you need to track objects based on their inheritance. So if they're inherited from an event handler object, you need to track the derived object. And then we also need to track objects via composition. If you have an object that has an event handler or is derived from one as a member object, you now need to track that object. So with this, we actually define sort of a set of classes of interest to us. So we define the set of classes of interest to us as the eventful types. And like I mentioned, so it's both from inheritance and composition that we define these. So an object is eventful if it inherits from an eventful object, or it's eventful if one of the member objects of the object is eventful, and that eventful object is disposed of when that object is disposed. So using the property of eventfulness, we can actually create the event types graph. So this is a graph that shows us how eventfulness propagates through the system. So here we have the event types graph for Gmail. We have each of the arcs each of the arcs is the event types relationship. It shows that if this class is eventful, then it will eventize that. So we have a DAG, and we have vertices representing the classes. Blue are eventful classes, and yellow are the ones that are not eventful. So starting purely from the event handler, we find that there's 1,100, more than 1,100 eventful classes in Gmail that we actually have to track during the JSWhiz phase. So how does JSWhiz work? Well, simply we actually do find the pattern occurrences in the code. We know the patterns. We basically create almost an AST matching where we know the order of AST nodes that we need to encounter to match a certain pattern. And we want to find this. And we do this in a flow and sensitive manner. If you see a creation somewhere and a disposal somewhere else, we assume it will happen. So we do not actually try and ensure for every object created. We try and do this purely at the AST level without any runtime information. We do this doing 2 transversals of the AST. In the first traversal, we define this event types relationship. and find the class of eventful object. In the second pass, we now track these eventful objects. So for each eventful object created, we want to ensure that it's being disposed of later. So we can only do this for a certain subclass. And we focus on the subclass which we can, are certain we can actually track. So for example, we ignored eventful objects stored into data structures and closures. This would require us to, for example, in the case of an array, track the array indices across the program to make sure they are disposed of when needed. We do not do this. So we ignore those objects we cannot set, we cannot track without generating spurious false positives. Then furthermore, we have to now track local objects that are being assigned to global variables. If you're creating an event handler object locally and then assigning it to a member function, these two actually now are an alias of each other. So whether the global one gets disposed of or the local one gets disposed of, it does get disposed of eventually. So we have to make sure that happens. And then furthermore, as you're progressing this ASD, it's very simple to just flag the unlisted with bound or anonymous functions, as well as the private class overriding. And so that's pretty simply what JSWhiz does. Now, if you look at the results, we tested JSWhiz on 7 Google applications. We looked at Gmail, Books, the Closure Library, Drive, Docs, Presentation, and Spreadsheet. Now, this was past the hackathon. So these were the leaks we detected after the previous ones have already been fixed that were identified in hackathon. So we identified 30 new leaks in Gmail alone, and 89 potential leaks across all these applications. And these leaks were actually fixed during internal code reviews. And so at the moment, JSWhiz runs without flagging any errors in any of these applications. So now the question is, yes, we have now identified 30 new leaks in Gmail. What is the effect of that? So again, if you look at real-world data, so this is from actual users of Gmail around the world, and we look at and these are, I have to mention, this is the total effects of all the internal efforts of Gmail. This is not necessarily specific to JSWhiz alone. We'll see a significant reduction in both the 95th and 99th percentile in memory usage of Gmail. Well, the median, so this is past the hackathon, the median is really stable. We see this huge reduction in the 91st percentile. So just to take a little step back before, how do we actually solve the JavaScript memory leak problem in general? I think there's 3 approaches we can in future follow to actually solve it. One, looking at the garbage collector, looking at the library, or looking actually at the developer. From the garbage collector point of view, we can actually make the JavaScript garbage collector more intelligent. We can make it aware of these patterns. Now, these patterns aren't closure specific. There are similar programs in jQuery libraries and other cross-browser JavaScript libraries. And I think this actually has the potential of polluting and convoluting the garbage collector with multiple patterns, and this might not be the correct avenue. The second approach is to look at the library. We can make the libraries and the way the libraries are written more clear to the garbage collector. We can expose the usage and liveness more clearly. We can also do things such as associating the usage and lifetime of an eventful object explicitly at creation, which allows us now to have additional semantic information required to flag such instances as the object graveyard. And then finally, I think also one where I think is probably actually in my personal opinion, the best place to go is actually at the actual developers. Make people aware of the fact that there are potential memory bloat problems in JavaScript. Because the first thing I hear whenever I mention memory leaks in JavaScript is, oh, that can't be. JavaScript is a garbage collected language. You cannot have memory leaks. And I think it's one of those cases where, yes, when you close the tab, your memory is reclaimed, but that's not sufficient. Memory bloat is a problem. And I think program awareness and tools such as JSWhiz will be really important in actually fixing some of these memory leak problems. So, in summary, we identified causes for JavaScript memory leaks using the closure library. We created JSWhiz, a compiler pass in the closure compiler. We statically identified 5 leak patterns identified. We see 30 new leaks in Gmail alone. 89 were identified across 7 large JavaScript applications. And we believe these fixes contributed to a significant reduction in the 95th percentile memory usage. And then finally, I'm also very happy to actually say that JSWhiz is currently used in Gmail in their pre-production testing. So whenever any new Gmail code is checked in, it's run through JSWhiz first to detect potential memory leaks. And when it was initially activated, so a couple of months after my internship, it found 6 additional memory leaks during the first run already. So thank you very much, and good questions.
Let's thank these people. All right, thanks for that exciting talk.
Ben Robert from Qualcomm Silicon Valley. Very interesting work, very impressive results. So I think one broad conclusion for me was that it looks like most of these leaks have to do with events and event handling, right? Did you ever come across any cases, or what's your thought about the ones that the leaks are not due to events? Just general JavaScript programming styles, because the problem is JavaScript programming styles are not good in general, and it's really hard to tell the programmers to change their styles. I was wondering if you have any thoughts on that.
So that's a very good question. I think sort of the data I was working with and the application I was working with was slightly skewed in the sense that they were developed by JavaScript compilers, developers at Google, so they have a very specific programming guidelines and programming methodology. I think probably one of the only case I remember where I was like, we should tell this programmer to change his style, was when they were doing, so there's one of the ways of doing it, there's a listen once call, whereby you associate an event with a certain callback, but it only listens once and then it removes itself. And then people were creating their own listen once implementations using interesting closure manipulations and things, but as you mentioned, these are valid JavaScript constructs. So we didn't look at that. And I think definitely, in general, like JavaScript applications in the wild, it would be a much more difficult problem. I think also but some of the ones you mentioned that are in the wild and advanced programming style, they are also of the case that they run for a couple of seconds and then you close it.
Right.
And so I think large applications such as Gmail, which runs for months, and such other applications, I think it has some better programming style. Actually, in terms of maintainability, the only way you can manage that is by very disciplined JavaScript programming. And to come back to your first question about did we discover any leaks not due to event handlers or event listeners, actually those were the ones we were focused on, as those were the ones that were identified. Somebody did mention that potentially some other native objects could also be a problem. We didn't see any of those, so potentially there are, because I think the sort of the pattern of you need to dispose this object and you're using it somewhere else. So that sort of the composition property of eventful objects, I think, extends beyond just being eventful.
Okay, thanks a lot.
John Cavazos, University of Delaware. This is really great work. I really like the work in your talk. I have a couple of questions. One is do you have any problems with false positives? And the second question is, have you thought about how profile information could improve the tool?
So with false positives, given we sort of focused more on objects, we could actually create a global identifier. So what I didn't mention here is the way we track them is in a way by trying to create a global identifier across the AST. The false positive instances we did find was when we actually tried to extend that to cases where we're looking at arrays or more complicated data structures, where we tried to say, oh, you're creating object I, whatever, and let's try and track the indices along with it, assuming the programmer has done his job. And in those instances, yes, we ran into quite a few false positives. The way we did this, I can only respond for the Gmail, because for Gmail we literally went through all of these leaks in detail. For the other applications, that was different teams. We just actually tried identification. But on Gmail, the ones we found, being conservative in what we're actually tracking in terms of variables we can literally follow. I think there was one instance, and that was due to a local variable escaping, and we weren't tracking it. But this was in the 6 that were identified later. So this wasn't in the initial 30. The 30 that were identified during my internship actually turned out to be real leaks. And as to how profiling information could help, so I think definitely you need both a static and a runtime approach. I think with JavaScript, given the dynamic nature of the language and the ability to change every single aspect of it at runtime, static analysis will never be sufficient. I think this is an engineering solution. We try to aim for like the 80%. Beyond that, I think you're going to do some real hard work online. So Probably just to clarify, do you mean profiling information as to looking at the memory usage of the applications running and triaging it back to the source code?
That's right.
So that is actually one of the things suggested internally by my boss's boss. And my feeling there was that if you try and go from the data back and you haven't actually inserted some debugging code into your data, it would be a very tough job. I think actually working back from the notice DOM objects that are leaking to where they were actually created is tough. Well, in our case, we literally tell a programmer, in this file, line so character free, you created this object and you never did anything with it. Well, you didn't dispose it. You did something with it, but not dispose.
Thanks.
Okay, I can thank the speaker again. Just to let you know, we're doing back-to-back sessions here, so Jack is going to introduce the next session.
Great. So